BC Calculus, Lesson 10.2, Taylor Series. This is going to get interesting. I have not played with this as much as I wanted to, but we are going to do what we did last lesson from a different perspective using calculus. So here's a polynomial, fourth degree, and I wanted to have all this behavior, to which you should say why, to which I will say give me a little bit and I'll show you. I'm going to do derivatives first. So p prime of x equals a1 plus 2 a2x plus 3 a3x squared plus 4 a4x to the third. P double prime equals 2a2 plus 6 a3x plus 12 a4x squared. P triple prime equals 6a3 plus 24 a to the fourth x, and I'll squeeze it in, p to the fourth derivative equals 24 a to the fourth. Time consuming. So we know that p of 0, I'm going to put it up here because I have a feeling I'll run out of space, equals 5. Well, if I plug in 0 to this equation, everything drops except a0. So we know that a0 equals 5. P prime of 0, put it where it belongs, equals 7. Well, a1 is the only one that won't drop out, so we get a1 equals 7. P double prime of 0, for some reason I can't draw p's today, is 11. So now we got to be careful, things just changed. Everything drops except the 2a2. a2 equals 11 over 2. P triple prime of 0 equals 13. a3 equals 13 over 6. P fourth derivative 0 equals 17. A to the fourth equals 17 over 24. And P of x will equal 5 plus 7x plus 11 over 2x squared plus 13 over 6x to the third plus 17 over 24 x to the fourth. So we can, using derivatives and the values we know at x equals 0, create a polynomial. This is a fourth degree polynomial. It's called a Taylor polynomial. We'll get into that in a minute. But we can create one that goes on forever if we look for the patterns like we've done previously. So we try natural log of 1 plus x. And that means we need to know the first 4 derivatives. So we're going to do this slightly differently. We'll just do it a piece at a time. P of 0 equals a naught. And that equals natural log of 1 plus 0, which is natural log of 1, which is 0. So a naught equals 0. P prime of 0 equals, as we saw earlier, a1. And we get the derivative of natural log of 1 plus x, 1 over 1 plus x. Remember, we're putting in 0. Get 1. a1 equals 1. P double prime of 0 equals negative 1. I guess I'll keep writing it the way I've been doing it. Equals a2 equals negative 1 over 1 plus x squared. Put in 0, we get negative 1. And this is where things got a little bit goofy. We saw that in the previous example. Once we got to this one, it was a2 equals negative 1, and we didn't actually say what was going on. That was 2 factorial, which is just negative 1 over 2. And if you think about derivatives, you can see why. Triple of 0 is going to equal a3. Well, actually, let's write that in. a2 over 2 factorial. a3 over 3 factorial. We get 1 over 1 plus x. No, we don't. We get 2. 1 plus x to the third. Put in 0, we get 2. So a3 is 2 over 6. Something's bothering me. I guess not. Just 1/3. And last but not least, looks like I should have left myself some room this time. P fourth derivative of 0 equals a to the 4th over 4 factorial equals, derivative is going to be negative 6 over 1 plus x to the 4th. Put in 0, we get negative 6, meaning a to the 4th equals negative 6 over 4 times 3 times 2 times 1 equals negative 1/4. Put it all together. P of x equals 0 minus, excuse me, document saving, minus x squared over 2. I'm going to put this down on the bottom. P of x equals 0 plus minus x squared over 2 plus x to the 3rd over 3 minus x to the 4th over 4. P of x equals negative x squared over 2 plus x to the 3rd over 3 minus x to the 4th over 4. I never do this, but I'm going to go back in my notes. And we said, hey, what's the power series for this? The natural log of 1 plus x. And we got a very familiar looking sequence series. X minus x squared over 2 plus x to the 3rd over 3 minus x to the 4th over 4, which I just realized I made a mistake on, but it's the same one, which is kind of nice I did that, so I know I made a mistake. Let me fix, even though I don't have quite the room for it. Up here, I'll just shove it up top. I missed my 1. Oops. 0 plus x minus, which is x minus x squared over 2 plus x to the 3rd over 3 minus x to the 4th over 4, which is a 4th degree Taylor polynomial. Now, what's a Taylor polynomial? We just made one. That's how you make it. That's what it is. A Taylor series would be as if we just went on forever and ever. which we could easily do if you notice a pattern there. Well, we'll come back to that. We'll talk about that a little bit later. So some complex stuff there. Taylor series goes on, never ends. How about a 7th order Taylor polynomial for sine of x? That sounds like just a jolly time. So f of x, I don't want to call it f of x, sine of 0 equals 0, derivative cosine of 0, which equals 1, derivative negative sine, I gotta write it all out, sine double prime of 0 equals negative sine of 0 equals 0. Sine third derivative of 0 equals derivative of negative sine is negative cosine. Negative 1. Sine to the fourth derivative of sine is sine of 0 equals 0. And if you look, you should recognize that we are right back where we started. So sine to the 5th of 0 will equal the next one down, 1. And sine to the 6th, why the parentheses? I'll let you figure that one out, because I just did, equals 0. So 1, 0, 1, 0, negative 1, 0, 1, 0, negative 1. It repeats, and it'll repeat forever. So, how do we put this in? Alright, well, we know. P to the x equals, we just plug it in. Our initial one is 0. Our A1, excuse me, I want to make sure I'm calling it right, I am, is 1 times x plus 0 times x squared over 2 factorial plus negative 1 times x to the third over 3 factorial. Gotta keep going here. Plus 0 times x to the fourth over 4 factorial. Plus, geez Louise, where the heck am I? 0, 1, 0, negative 1, 0, 1 times x to the fifth over 5 factorial. Plus 0 times x to the sixth over 6 factorial. We're going to go 7th degree, so we actually had to do this 8 times, which I didn't do, but we know the pattern. 0, 1, 0, negative 1, 0, 1, 0, plus negative 1 times x to the 7th over 7 factorial. Rewrite it, because there's a lot of zeros in there. I'm calling this p of x. Sine of x. Sine of x is equal to x minus x to the third over, I'll leave it as factorial, 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial. So what's the Taylor series for sine of x? Now that we've done the first bunch of terms, well, we should be able to recognize it. Sum from n equals 0 to infinity. And I'd love to say I'm smart enough to figure this out. The reality is I'm not. It's very challenging stuff. Since it goes every odd term, we have to put it as an x to the 2 n plus 1. Since it alternates, we have to go in with negative 1 to the n. And on the bottom, we have factorials, which doesn't matter if it alternates or not, but it goes up quickly. So we have a 2n plus 1 factorial. And we check it, of course. The 0th term is x to the first over 1 times -1 to the 0 vanishes, x, done. Put in 1, we get a negative, check. On the bottom we get a 2 plus 1 is 3 factorial, check. On the top we get an x to the third, check. Now the question is, if I put in sine of radians pi over 6, which is between -1 and 1, and then I put in pi over 6 minus pi over 6 to the third over 6. Yeah, I'll write out I'll leave the factorials. 3 factorial dot dot dot. How close will that be to the real sine of pi over 6? Well, we're going to have to go find out. It should be very, very close. It should be a good approximation. It's kind of fascinating. Pi over 6, of course, is 30 degrees, so we should get about 0.5. So I don't have to check the sine of pi over 6, although I do have to make sure my calculator is in radians. That should do it. Mode. Yep. Quit. And this is going to be challenging. And what the heck? Second pi divided by 6 minus second pi divided by 6 to the third divided by 3 factorial. 3 times 2 is 6 plus parentheses second pi divided by 6 to the fifth divided by 5 factorial. That's 5 times 4. 20 times 6 is 120. Minus, this is our last term, thank goodness, because this is getting very tedious, pi divided by 6 to the 7th divided by, and forget trying to do 7 factorial for me personally. Math. I think it's probability, I'll find it. 4. Good. How about that? 0.4999999. Sine of pi over 6. 0.5. We've discovered some fundamental law of nature here that functions can be represented by polynomials. That freaks me out. Did the first time I did this too. So Taylor series is the general term. Maclaurin is when it's centered at x equals 0. We're going to focus on x equals 0 for a while. We will get around to getting into other series that are focused at an x equals a. So find the fourth order Taylor polynomial approximates y equals cosine of 2x near x equals 0. As we said earlier, it's going to be extremely tedious doing all these over and over and over again. Here's what we're going to get to eventually. We have this written down somewhere else. That cosine of x equals 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus dot 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 dot. If we want the fourth order, then we're just going to that term there. So we only need these. Anyway, and what goes in for 2x, well, we've done something similar to this before. Cosine of 2x equals 1 minus 2x squared over 2 plus 2x to the fourth over 4 times 3 times 2 equals 1 minus 2x squared plus 2x to the fourth over 3. Notice how much easier it is. I'll give you a chart of everything so you have something to work off of and how much you have to memorize for the AP exam. I don't want to tell you now because it'll make you cry. But it gives you a real nice approximation. At this point you should say, well, whoa, 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 what happened to that interval of convergence? To which I say, yeah, we'll get to that. Really, 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 really good point. Here's where we start to kind of touch on it, to kind of talk about it. how accurate do we have to be for like just sine of 13? This is the sine series, which we did earlier, and we would have to just blast out. How many terms do we need? We would have to go with sine of, if we're doing 13 degrees, of course we want to put this in as radians. Oh no, it's just sine of 13 radians. I thought it was 13 degrees, my bad. 13 equals, here's r, 13 minus 13 to the 3 over 13 to the third over 3 factorial plus 13 to the 5th over 5 factorial minus 13 to the 7th over 7 factorial plus, and we would have to just blast this out, and every time we do a term we would have to compare it to what we get on our calculator, and I will leave that one up to you. Again, it's fairly tedious, otherwise I'd give it a shot. But it's an interesting concept. How accurate do we need to be? We're going to spend a lot of time talking about that. We want our error to be less than 0.001, then we need 7 terms, 6 terms, 5 terms, whatever it is. So we can approximate a Taylor series at x equals a. This is not called a Maclaurin series. A Maclaurin is a Taylor series at x equals 0. And it's just got a big ugly formula, which I didn't bother typing because you'll recognize it's the same deal. So we need e to the x series before we run with this. We could do all the nastiness, but we've already done that. So I will put this out there. E to the x equals 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus dot 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 dot. So how do we do it when it's not centered at 0? Alright, let's find out. First off, put in 2 e squared one plus, and this is where things get goofy fast. Excuse me. Nearly goofed that up. I have to actually go and derive this. Yeah, I'm going to think about how I want to do this. Yeah, since we're not centered anymore, we have to rewrite this differently. So let me figure it out. It's, f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared dot dot dot. So f of a, I put in 2, I get e squared. Seems kind of dumb. E squared equals e squared. So actually we'll do this. And remember, we're saying that it's centered at x equals 2, not that it equals x equals 2. So we can go left and right of there and get pretty close. Plus derivative of f with a in it, e squared, x minus 2 plus e squared over 2 factorial, x minus 2 squared plus e squared over 3 factorial, x minus 2 to the third, dot 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 dot. So we would get the sum from k equals 0 to infinity of e squared over k factorial x minus 2 to the k. So you could find e to the 2.1 using this because it's centered at 2. And that's how we handle this whole x equals 0 versus x equals a thing. Let's do 2 last examples. And then I've got a whole thing printed out for you to make your life hopefully a little bit easier. Apologize for the length of this video. Third order Taylor polynomial for blah, 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 blah. So at x equals 0, it's already written. So nothing changes. It's pretty straightforward. It's its own third order, fourth order, blah, blah, blah. So for third order, it's written. So this is just now at x equals 1, this gets a little sticky. We got to do the whole derivative thing. F of 1 equals 2 times 1 to the third minus 3 times 1 squared plus 4 times 1 minus 5 equals, do some math, negative 2. F prime of 1 equals 6 1 squared minus 6 times 1 plus 4 equals 4. F prime of double prime of 1 equals 12 times 1 minus 6 equals 6. And F triple prime of 1 equals 12. So Taylor polynomial, third degree, negative 2 plus 4 times x minus 1 plus 6 over 2 factorial x minus 1 squared plus, goodness gracious, 12 over 3 factorial x minus 1 to the third. We can blast this out and keep simplifying. So let's put the big stuff up front. That would be 2 x minus 1 to the third plus 3 x minus 1 squared plus 4 times x minus 1 minus 2. So it agrees with the original function at every value of x, but it's written in powers of x minus 1. If we blast this out, we would get 2x to the third minus 3x squared plus 4x minus 5. I'll leave that one for you if you want to try it. But you can definitely see it's a 2 out front. And no, you can't. Well, yeah, you get a negative 1, negative 1, negative 4, negative 2. One of those get, oh, positive 1. They cancel out. Negative 4 minus 2. I'm not seeing it. Oh, 3 and 2. Yeah, that's going to work out because of the coefficients. So there's a lot cooking there. Last but not least, here are the most common Maclaurin series. Have them handy. Arctangent. Hey, didn't we do that one? Natural log of 1 plus x. Cosine of x equals 1. Sine of x. E to the x. 1 over 1 minus x. 1 over 1 plus x. These are all set up for at x equals 0. And these give the intervals of convergence, which we have deliberately avoided more coming to a theater near you. That's a lot of information. As I always like to say, happy mathing, but in this case, good luck.